Hello everyone. Today I'm going to talk about trapezoidal decomposition and its applications. What exactly is trapezoidal decomposition? It is a computational geometry algorithm that what it does exactly is given a planar subdivision, in simple terms, let's say a map which is formed by n line segments, we need to break this map into a set of trapeziums. That is what we are doing in this algorithm. We are decomposing the given map into a set of trapeziums. So where can it be used exactly? Like, the most important application of this algorithm is in point location problem, which we will discuss in the next slide. And another thing is line segment intersection. Given n line segments, we can point out all the segment intersections in expected time of order of n log n plus k, which is faster than its line alternative line sweep algorithm. We can also use it in triangulation refinement. The problem of triangulation is very similar to trapezoidal decomposition. In a similar way, if a map is given, we need to break the map into a set of triangles. So how can you do it? If you know trapezoidal decomposition, then you first break the map into trapeziums and then you join any one of the diagonal of each trapezium that has been formed. Then each trapezium is divided into two triangles, hence the entire map is now divided into triangles. So this is how triangulation can be done with the help of trapezoidal decomposition. And this algorithm is also one of the methods of making Voronoi diagrams, and Voronoi diagrams have a huge set of applications. You can find the closest point in a set of points just by locating the cell to which it belongs. Now given this image is an example of Voronoi diagram. You can do a research on this topic if you want, but I'm not going into this topic in this lecture. So coming back to the point location problem, the point location problem is given n line segments like in this example, we need to given a point P. By given I mean if the coordinates of the point P are given, we need to locate the point by telling which region it belongs to. And slab decomposition algorithm is the most simplest way of doing this. Now actually I have taken a very simple case. I can take even a complex planar subdivision other than this, and but the assumptions are that no different endpoints are having the same x coordinate, even though we can handle the situation just by rotating the entire map, because by rotating we don't change the region to which the point belongs. Now what we do is we divide the entire region into slabs by passing vertical lines through each vertex. Now we know that the entire region is divided into slab. If we look closer to each slab, we have that at max n lines can be passing through the entire slab from the extreme left to the extreme right of the slab without stopping in between, and we already know that no intersections between two lines are possible within this slab. So we have a particular kind of ordering here. We can order these lines for other purpose, which I will going to be discussed. If we want to find out the region of the point P given by this, we know that in this case this is the region where the point P belongs, the specific region. What we do is we first do binary search to find out which slab we want by the x coordinate of this point P in order of log n time, and then when we get this slab, within this slab we do another binary search for the exact region where the point P exists. So the time complexity of this point query is here order of log n, because there are two binary searches. Combination is order of log n, but the space complexity is a problem here, because at max, in worst case, each slab can have n lines and there are n slabs like this. Because we want this to store the sorted order to do the binary search, we need order of n square space with each slab having order of n space. So various algorithms have tried to obtain a better solution to this problem. Like we have monotonic subdivisions which have approximately order of n space complexity, but the query time has been increased to order of log square n. We have another algorithm which is based on all the triangulated subdivisions. The algorithm name is Kirkpatrick. You can search it in net. But today's discussion is trapezoidal decomposition, so I'm going to stick with it. Kirkpatrick algorithm is also similarly good because its complexity is also order of log n and space complexity is order of n, but today we are going to talk about trapezoidal decomposition. So trapezoidal decomposition is a randomized algorithm I will tell you why it is randomized in some time, but basically the idea is to shoot bullets from each vertex to the top and bottom, which stop as soon as they hit another line or the bounding box. You can see that each vertex, you can see that the bullets that are being shot hit to the other line segment and stop there. So the regions that are formed, every region that has been formed here is a trapezium. Even the triangle here is a trapezium with one of its sides 0. The rectangle is a trapezium with both equal sides, equal and opposite sides. So we have divided the given map into a set of trapezium, that is our algorithm. But in these 15 trapeziums, given a point, we need to find out whether it is in 10th trapezium or 13th trapezium. How can we find this? Because now we can't apply binary search, but we should apply something very similar to binary search. For this, we maintain a data structure called point location data structure to answer specifically the point location queries. So this data structure is very similar to binary search, but it has not a very similar but not exactly a binary search tree. It has three types of nodes: a point node, a line node, and a leaf node. Now a point node is something that represents a point, and the left child of a point node can be another point or a line or a leaf node which lies to the left of the point in the graph, and the right child can be anything that lies to the right of the point. A line node, you can think of it as a pointer to a line segment. Basically it represents a line segment, and the left child can be anything that lies to the above of it, and the right child can be anything that lies to the below of it. This will be made clear by the example that I am going to show in the next slide. And a leaf node is a region, because we are basically trying to search for a region in this algorithm, in this data structure. After we reach a region, we are no longer going to proceed further. So every leaf node will be a region in here. And another interesting fact is, if there is a line and we enter the scope of line segment only when we know that the x coordinate of the query point lies to this left extreme endpoint of the. So basically the query point's x coordinate should lie between the both endpoints of the line segment. Then we go to the scope of line segment and check whether the query point is above or below to the line segment. Now to make it clear, we have an example here, very simple example with two line segments. So first what we do is we construct the trapezoidal decomposition, and then we label the lines and then the regions. So we have got 7 trapeziums here. So we start our construction with point P1. Here I am going to represent point nodes with the circles, line nodes with pentagons, and region nodes with, or leaf nodes with, squares. Another interesting thing is the way we construct the entire data structure for a bigger example is we randomly select one of the edge and include it in the existing data structure and update the data structure. I will show how to update it after we complete first building the data structure for this. So from point P1, what will be the left child of P1? We have to the left of P1 only region A, nothing else. So left child of P1 is A. On the right of P1 we have points Q1, P2 and Q2. So here I have a choice. I can select any one of the three. There is no mistake in selecting any one. So depending on what you choose at this point, your construction may look a little different, and it is possible to have a different data structure for the same example. So I am going to choose Q1, and to the left of Q1 and to the right of P1, because we are already on the right branch of P1, what do we have? We have the line segment S1 here. To the right of P1 and to the left of Q1 we have the line segment S1 here. So we have the line segment S1, and above S1 we have B, and below S1 we have multiple. We have C, we have D, we have F. So actually we are going to choose a point here. So below S1 we are having a point P2, and to the left side of P2, our scope is now left side of P2, and we are already looking to the right side of P1 and below S1. So we have the region C1, and to the right side of P2 and left side of Q1 is our scope. We have this line segment S2, and in this scope above S2 we are having D, and below S2 we are having F. Now we go to the right side of Q1 and see that there is the point Q2, and to the left side of Q2 and right side of Q1 we are having the segment, a portion of the segment S2, and above S2 in this portion, that is right side of Q2 Q1 and left side of Q2 in this portion of the line segment S2. Above S2 we are having E and below S2 we are having F. So we just keep a connection. Right side of Q2 we are having just the region G. So our data structure is complete right now. So any point is given, we can just go through this data structure till we reach a leaf node, and that will be the region to which the point belongs to. Now let's say we added a line segment because we need the update step. We see that the trapezium C, D, E and G are being affected now. So we need to remove them because they are no longer valid. So we will first label this line and then remove them. Now we reconstruct the trapezoidal decomposition to suit the new example. So after we reconstruct this, let us just label the new trapeziums that have been formed: H, J, I, L, K, M, N. So now how can we update this? We just update the nodes, the leaf nodes that have been affected, like C, D, E and G have been affected. So let's remove C. And now what is to the left side of P2 in this portion, that is below S1 and right side of P1? We have the point P3. And what is to the left side of P3? We have H, and right side of P3 and left side of P2 we have this portion of S3 specifically. So in this portion above S3 we are having I and below S3 we are having J. So this is completed. Then we go to the next affected trapezium, that is D, and we remove D, and now we are having above S2 in this portion we are having L, I, K, and below S1, because we are specifically looking below S1. In this portion we are having these many things. So what we do is, exactly, there is a point S3 here, and above S3 we have I and below S3 we have L in this area. Then we remove E and replace it with, let's see, above S2 and to the right side of Q1, left side of Q2. This is our region of portion S2. Above S2 we are having S3, and in this area above S3 we are having K and below S3 we are having L. Next we remove G. Then right side of Q2 we are having point Q3. This is a simple case. And left side of Q3 and right side of Q2, in this area we are having this portion of segment S3, and in this area we are above S3 we are having K and below S3 we are having M, and to the right side of Q3 we are having N. So we have updated the data structure. It looks a little bit big now, and if a planar subdivision with n line segments is given, then what we do is, initially everything is empty, we randomly select an edge and construct the data structure for that, and we keep updating by randomly adding edges till all the n segments are completed. So now that we know this algorithm to find out the region which this point belongs to, our given point, what can be the applications of it? Like in this graph, given my point, I can know that I am in this region 7, but how does this help me? What this graph can be? This graph can be actually anything. It could be a real map, and you could know your region in this map. You could know your street or your area where you are living, just in order of n log n time basically. And or it could be a rainfall distribution. If you own a farm and you want to know whether your farm lies in the region of high rainfall or water scarcity, so that you can plant something if water is less, you can know that. Or if you have a mineral mining area and you want to know whether your land mining area lies in the region having high mineral density in the soil, you can know that. Or whether your region is affected by some weather forecast, that kind of a thing. You get the idea. And also in AutoCAD software, you can see that there are actually a lot of regions here. This is a very huge planar subdivision. If you click with mouse on anywhere, the entire bounded region corresponding to that area is highlighted in the software. This is also done by this application. And robotic motion planning, like given a starting point and an ending point, the robot can plan the path even in the presence of obstacles like this. Actually, this is not a direct application of trapezoidal decomposition, but this is an application through Warner diagrams, so it becomes a basic kind of indirect applications. And there are many more algorithms which have trapezoidal decomposition as a part of them. So indirectly their applications become applications of trapezoidal decomposition. So there are a lot of indirect applications. Okay, thank you. I hope you understood, and just try to go through these references. I will post them in the down below link below the video. You can go through these references for additional knowledge if you want. Thank you.